Hello everyone, I'm Tian from Tian University, China. My topic is making Streett Determinization tight. This is the main points of our presentation. First, we introduce the automata over infinite words. Automata over infinite words are the same as the finite ones, except for the acceptance condition. Here are three kinds of acceptance conditions: Streett, Rabin, and parity. Different kinds of automata are denoted in this form. The first letter stands for deterministic or non-deterministic. The second stands for Streett, Rabin, or parity. And the third is automata. We also have the transition version. Background and motivation. Determinization constructions of Streett automata have been investigated for decades. The best results for determinization constructions to Rabin and parity automata have been presented in references. As for the state lower bound of Streett determinization to Rabin automata, an asymptotical tight bound has been proved. But what about the exact one? To parity automata, the best state lower bound haven't been improved for a long time. There is a big gap between the upper and lower bounds. Therefore, it is challenging to make the state complexity for Streett determinization construction tight or tighter. Before presenting our determinization constructions, we first introduce H subtree and layer H subtrees. An H subtree is a labeled ordered tree, while T0 is an ordered tree, and V is the set of all nodes in T0. As an example, the left figure shows an NSA with 5 states and 3 Streett pies. The right figure is an ordered tree with 12 nodes of the NSA. L is a state label of nodes, which satisfies two conditions. In the figure, the state labels are shown in nodes. H is an index label, which annotates every node with a set of indices from chi and satisfies the following two conditions. In the figure, the index labels are shown in blue. Min is used to decrease the combination of index labels, since there may exist a situation that some G of a Streett pi is contained by another G prime. If G prime has been checked, it is redundant to further check G. This is an example which shows the calculation process of min. Store is an additional structure ordering on nodes, which determines the order of siblings according to the index labels. In the figure, all nodes satisfies structuring ordering. Mn is a naming scheme of nodes, which is the core of our construction. Each node is named depending only on its index label and position in the tree, which makes the state complexity decrease. All of these components make up an H-suffer tree. An example of an H-suffer tree is illustrated in the figure, and the names of nodes are given in red. As for the layer H-suffer tree, it is an H-suffer tree with layer, which stores the generation order of nodes. Every node in layer is represented by its name for simplicity. Now we present the determinization of Streett automata. For the construction from NSA to DRTA, we use an example to show the transformation from an H-suffer tree to another one. The left figure shows all the transitions for an input letter. Step 1. Update state labels. After this step, state labels of all nodes are replaced. Step 2. Create siblings by applying the following transformations. The nodes without names are new created. In the example, there are 7 new nodes. Then rearranging sibling nodes by the structural ordering. In this example, the last node in the second level is relocated to the 5th position. After this step, new siblings are created, and every node observes the structure ordering. The state labels of the nodes in green will be deleted in the next step. Step 3. Horizontal merge. After the operation, the state labels of the siblings are pairwise disjoint. Then remove each node whose state label is empty. A removed node whose name is defined is called rejecting. 11 empty nodes are removed in this example. As a result, there exists no empty node. Nevertheless, there may exist a node which is equal to each of its children in index label. Next, we define the rejecting signature of the transition, including rejecting nodes. There are 9 rejecting nodes in this example. We add their names to the rejecting signature. Step 4. Vertical merge. If a node is equal to each of its children in index label, then remove all the descendants of the node. The nodes whose descendants have thus been removed are called accepting. The node named 2 power 2 follows the rule. It is accepting in this example. Next, we define the accepting signature of the transition, accepting nodes included. There are only 1 accepting node in this example. We add its name to accepting signature. However, the names of nodes might not follow the naming scheme. The nodes that will be renamed in the next step are drawn in red. Step 5. Rename nodes whose names are defined. the nodes which should be renamed are also rejecting. As for this example, there is a renamed node, 2 power 2. Add it to rejecting signature. After this step, in this example, all nodes observe the naming scheming. Then the resultant tree will spawn in the next step. Step 6. Create children by the following rule. After this operation, children of each leaf are created. Then define names of the nodes which have not been named yet. In this example, each node has unique name written in red. By the above steps, a new H sufferer tree is obtained, and the accepting and rejecting signatures are part of transition relation. Based on the 6-step procedure, a DRTA-RT can be constructed, whose states are H sufferer trees, and the acceptance condition is a set of wrapping pairs. In each wrapping pair, the indexed I ranges over the names appearing in the H sufferer trees. The first element is the set of transitions through which node tau with name being I is accepting, while the second is the set of transitions through which node tau with name being I is rejecting. Further, we prove that the language of RT is equal to the language of S, and RT has less states compared with the best known result. For the construction from NSA to DPTA, it is similar to the construction from NSA to DRTA. The difference is the definition of signature. In the construction from NSA to DPTA, the signature is defined by the node with the minimal position in the layer who accepting or rejecting. Then, a DPTA-PT can be constructed, whose states are layer H sufferer trees, and the acceptance condition is a set of transition sites named priorities. The priorities with even indices are sets of transitions whose first element of signature is accepting, while the priorities with odd indices are sets of transitions whose first element of signature is rejecting, and other transitions are included in the last priority. Further, we prove that the language of RT is equal to the language of S, and PT has smaller states than the result of Pitman's. Next, we prove lower bounds state complexity for the determinization construction. By the I game, we prove the tight and asymptotical tight state lower bounds. We first introduce the definition of L game for two players, Adam and even, which is a tuple with positions, alphabet, and moves. A play result is an infinite word, even once if this word is in winning condition, The figure depicts a L game for two players. A strategy for the player X is a function which depends on the finite history of the play, which tells player X what move he or she should take. And a strategy for the player X is winning if X wins every play, provided that he or she plays according to the strategy. The memory of a strategy refers to the size of information that the player needs to record in order to win. As for the example, if the winning condition is a formula, even must record T as to win. Thus, the memory is 2. There is a proposition that if Eva wins an L game and requests memory M for that, then every deterministic wrapping automata for L has size at least M. Then we present a special automata named full Streett automata. The difference from the general Streett automata is the alphabet, which is defined by this formula. The full Streett automata contains all kinds of transitions. According to the proposition, we will use the full Streett automata to prove the state lower bounds. Thus, to prove the lower bound state complexity for determinization construction from NSA to DRA or DRTA, our goal is to construct an L game satisfying the two conditions. Before constructing the L game, we define the beneficial words first. The word is beneficial for winning if there exists a node satisfying one of the three conditions written by Wright, which makes the node develop towards according during the transition. In addition, these two truths coincide on every node, like graphically to the left of the node, and no node to the left or equal to the node is rejected. Then the L game is constructed, which has a flower shape. The central position is controlled by Eva, and the petals belong to Adam. Moreover, each petal corresponds to each cipher tree. The running procedure of the L game is that Adam moves to the center first. Then Eva chooses to go to some petal HI by playing an empty letter. Adam resolves to the center by playing a beneficial word U from HI. Repeat this process. An infinite word connected by beneficial words will be outputted, and the word is accepting. Thus, Eva wins the L game with a strategy like running in RT, structured by each cipher trace, and the memory of the strategy is HN. Assume Eva has a winning strategy with less memory, i.e., some petal H will never reach. However, for any two different H cipher trees H and H prime, there exists a beneficial word U from H prime such that H is obtained after reading U from either H or H prime, and there is no accepting node in the transformation from H to H prime. So Adam wins the L game lacking a petal by playing the above U when in H prime. Therefore, Eva cannot win the original L game with less memory. Thus, the lower bound state complexity for the determinization construction from NSA to DRTA or DRA is proved and described by the theorem. This theorem means that the proved lower bound state complexity for the determinization construction from DSA to DRTA or DRA exactly matches the state complexity of the proposed determinization construction by each cipher trace. Further, to prove the lower bound state complexity for determinization construction from NSA to DPTA, we will also construct an approximate L game. The difference is that this L game recognizes the complement of the language of full Streett automata. The L game also has a flower shape, but the petals are subset of states of PT, which satisfy that the nodes who have the same position in any two layer H cipher trace have the same index labels. Also, we define the beneficial words. The word is beneficial for winning if there exists a node satisfies one of the two conditions written in red, which makes the node develop towards rejecting during the transition. In addition, these two trees coincide on every node left of the node in the layer. Based on the approach improving the state complexity from NSA to DRA, we can obtain this lemma. According to the relationship between Rabin and Streett automata, the lower bound state complexity for the determinization construction from NSA to DPTA or DPA is proved and described by the theorem. This theorem means that the proved lower bound state complexity for the determinization construction from NSA to DPTA or DPA is the same as the state complexity of the proposed determinization construction by layer H cipher trace in the exponent. Finally, let's summarize. We present improvement determinization constructions named H cipher trace and layer H cipher trace from NSA to DRTA and DPTA respectively. Further, we prove a tight state lower bound from NSA to DRTA. Also, we put forward an asymptotically state complexity for NSA to DPTA. That's all. Thank you for your attention.